last time we have discussed about properties of, no, not properties of estimators. We've seen interval estimator and point estimators, and we've discussed how to get one of the interval estimator, that is the interval around the population mean, right? So what we've done is we were not aware of what population mean actually is. In spite of that, we were able to get some interval with some amount of confidence around population mean. We've also discussed that this interval has two critical aspects to it. One is the confidence that we associate with the interval, and second is the width of the interval. And we've concluded by saying that if we actually raise sample size to some extent, then the confidence would also be high and the width of the interval would also be reasonably narrow, right? So in today's class, what we shall do is we shall look at properties of estimators, right? What we have seen so far is there is a parameter value. Parameter we denote generically as theta, right? Any value of parameter generically we denote as theta, and statistics is, or the estimator is denoted by theta. Okay, so theta is a parameter to be estimated. So mu, sigma square, the population variance covariance matrix, anything is my parameter. The correlation or population variance covariance or variances themselves would be my theta, and theta hat is an estimator of that theta. Now the point is, theta hat should have certain properties so that I would trust that theta hat is a better estimator of a theta. So what I want is this theta hat to be a good estimator of theta, a estimator that I would perhaps want to use to estimate theta, right? So theta hat should have certain properties. These properties are divided broadly into two classes. One is called as small sample properties and second is called as large sample properties. Okay. Initially we'll have a look at small sample properties and then we move to the large sample properties. Okay. These properties state what theta should be, so what theta hat should be, how theta hat should behave, and then if theta hat is behaving accordingly, then we say that theta hat has that particular property. Okay. Now let's look at first property, unbiasedness. Okay. Or unbiased estimator. Okay, unbiased estimator. What is the unbiased estimator? A theta hat is called as unbiased estimator of theta. Unbiased estimator of theta if the expectation theta hat is equal to theta. Okay, when expectation of theta hat is equal to theta, theta hat is called as unbiased estimator of theta. Okay, which means that if we take the expectation of theta hat minus theta would be 0. Would be 0. So there is no bias. Or if we do, if we want to know bias of theta hat, we do a simple thing. We take expectation of theta hat and we subtract this expectation theta hat minus theta would be the bias in theta. If this bias equals to 0, theta hat would be called as unbiased estimator of theta, right? Now suppose this is the value of theta, which is an unknown value, okay, and we use estimator theta hat to estimate this value. So there are times I would get estimator values above theta, right, or below theta. Say for example, my population parameter is population mean. Okay, so suppose I'm measuring power distance of Hofstede's conceptualization. You're aware that Gerd Hofstede talked about cultural dimension in two of his most important contributions. First is culture's consequences, the second one is cultural organization. Okay, so in these two books, he spoke about the various dimensions alongside which cultures can be divided and we can understand them. And so one of the dimension is, say, power distance. Okay, now power distance, say suppose I want to know what is the population mean of power distance in say Mumbai. Okay, now this value would be mu theta, okay, a population parameter which is not known to me. Now what I will do, I will take a sample, compute the mean. Now that mean can actually be randomly above or below the value of population mean. If I get a sample's mean, if I take a random sample from the population with replacement, then there is no systematic way in which I would obtain a sample's mean either above or below population's mean. It would randomly either be above the population mean or it would randomly below the population mean. There is no reason that I would consistently, or there is a high chance of getting values smaller than the mean, or there is a high chance of getting values larger than the mean. This will not happen. If I consistently get values, or if there is a high chance of getting values larger than the population mean, then the property of unbiasedness is in danger. Not necessarily that it would be in trouble, but the whole point is, if this is happening, then the chance, then the expectation of those values. So suppose I get some few thousand means of my few thousand samples from Mumbai city, and those are mean values of power distance for few thousand samples. The mean of those samples, sample mean, so I have a distribution of the sample means, and that distribution would look like this, and the mean of that distribution is theta, that is mu, right, in case of population mean. Which means that the chance of getting value higher or lower is identical, means that expectation of all the values that sample can take, expectation of all the values that a sample can take would be equal to the population's value. Expectation of all the means would be equal to population's mean, right? Means it is unbiased. Okay, it is unbiased. So this theta is equal to expectation of theta hat. So I have theta hat. If I have large number of theta hats, and if I do, or all possible theta hats, and if I take an expectation of those theta hats, that is, take an average of those theta hat values, then that would be theta, right? That's what unbiasedness means, right? Well, that doesn't really mean that the likelihood of getting a value above and likelihood of a value getting below is exactly identical. It might not, because expectation can turn around to theta, expectation of theta hat can turn around to any theta, even if the chances are unequal, even if the distribution is skewed. Distributions are not necessarily symmetrical to get a value of theta, right? The next property, any issue about this particular property? No? Okay. There's one point that I perhaps wish to make. Now, the most popular and known estimator that is unbiased is sample mean. Sample mean is X bar. X bar is estimating what? Population mean or mu. Now, sample mean X bar is a unbiased estimator of population mean. So if I take all possible sample means and take an expectation of those sample means, then that would be equal to mu. That is, expectation theta hat is equal to theta. Now, one of the very well known biased estimator of the population value is sample variance. Or S square. S square estimates sigma square, right? Now, how do we get S square? We get S square by summation x minus x bar bracket square upon n, right? This is how I get S square, and if I square root it, then it would be the standard deviation, right? Now, S square, this S square is a biased S square. Is a biased S square. Now, I'm not working out the proof of the magnitude. How do I get the bias of it? But I can compute the bias that is there in this S square, and that is of the. So if I want S square unbiased, then I get it by n upon n minus 1 into S square bias, which means I would perhaps be writing n upon n minus 1 into, say, summation x minus x bar bracket square upon n, which actually can be written as summation x minus x bar bracket square upon n minus 1. These two n would cancel, and so what remains in the denominator is n minus 1. So, what is the difference? The difference is for S square, the sample S square is a biased estimator. So, when variance, sample's variance is obtained with the numerator n, that is sample size being the numerator, this is a biased estimator of the population's variance. So if I am using denominator n, then I am actually bringing bias to my estimator. So what is the proportion of bias? So how do I convert this biased estimator into an unbiased estimator? It's known, which I am not working through, is n upon n minus 1 multiplied by S square bias, which means n upon n minus 1 into the variance. These two n would get cancelled, and summation x minus x bar bracket square upon n minus 1 would be the unbiased estimator of sample's variance. So if this is to be unbiased, I have to take the denominator as n minus 1. And so when we compute variance, we must keep this in mind, that we should be using n minus 1 as a denominator than n, because whenever we are actually using the sample's variance as an estimator of a population's variance. If you are not interested in using it as an estimator of population variance, then you might as well use n as a denominator. So there is a difference between the two S squares that we get. This is a biased estimator, which is a sample variance, and this is an unbiased estimator, which is an estimator of a population variance. Okay, so this is the difference between the two variances that we compute. So uh, what are we effectively doing? We are making the variance slightly larger because we are dividing it by a slightly smaller amount, right? You would also realize that this fraction would become smaller and smaller as n becomes larger and larger. This fraction would be really very large value when n is small, but this fraction would be really a small value when n is really very large. Okay, so dividing 1000 by 999 is a very small difference between n and this adjustment is very close to 1. Okay, but if I divide 10 by 9, then that's far away from 1, right? So that's the whole point, right? And so the thing that we need to understand is when you use samples variance to estimate population's variance, we are actually underestimating the population variance, and so we need to actually increase the size of the estimator, and that is done by actually reducing the size of the denominator. When we shall discuss analysis of variance, perhaps we shall discuss this in detail. The distribution of, while even discussing TTS, we shall discuss this in detail. The distribution of sample mean and the distribution of sample variance, biased, unbiased of all the times. Okay. Any question? The only question that I am not answering as of now is why this is n upon n minus 1. The next property is minimum variance. Minimum variance. Suppose I have an estimator of theta, which is theta hat 1. I have one estimator of theta, which I call theta hat 1, is an estimator of theta. Okay, and if I can say that variance of theta hat 1 is smaller than variance of theta hat 2, okay, if I can say that variance of theta hat 1 is smaller than or at the most equal to variance of theta hat 2, then where theta hat 2 is any other estimator of theta, where theta hat 2 is any other estimator of theta, then theta hat 1 is called as minimum variance estimator. Okay? See, give theta hat 1 as the estimator of theta, as the estimator of theta. So the variance of theta hat 1 has to be smaller than or equal to theta hat 2, where theta hat 2 is any other estimator of theta. Okay, now so suppose this is theta, this is theta hat 1, and this is theta hat 2. Again, both of them don't have a mean around theta. I'm not concerned about unbiasedness basically. Okay, I'm only concerned about the fact that they have different variances. Okay, this is say theta hat 2, this is say theta hat 3, and so on and so forth. Okay, so this one is theta hat 1. Now if theta hat 1 has now look at the variance of theta hat 1. It has got a smaller variance. as compared to all other estimators. Theta hat 2, 3, 4, 5, I'm not drawing all of them. But what does it mean? So theta hat 1 would be called as minimum variance estimator. Okay. Now, what is the advantage of this? It means that if this particular estimator has a smallest variance among all the estimators of theta, then which means that if I actually take a value of that estimator, if I take a sample and get a value from the estimator, the chance that that value would be those values would be tightly surrounded around the true value of the population parameter is much higher than the chance that those values would be far away. Suppose I take theta hat 3, there would be some value that would be this far, right? Whereas if I take theta hat 1 as the estimator of theta, then the chance that I would get the values this far is also very low. So I get values. So see, the point is, when I actually draw samples and get values of estimator, the estimators would not be theta. They would be around theta, right? My sample mean can never be population mean, right? It will be value higher than or lower than population's mean. Okay, and so I want values that are closer to the population mean. Okay, not really far away from population. When the variances of the estimators are larger, then the chance that I would get a value far away from population mean is high. When the variances of the estimators are smaller, then the chance that I would get a value far away from the population's value is smaller, right? And so I look for a minimum variance estimator. Okay, I look for a minimum variance estimator. Now, the next property, any question? Next property is efficiency. Efficient estimators. Now, what is the efficient estimator? Efficient estimator is also called as best unbiased estimator. An estimator that has minimum variance is called as best estimator. Okay, the estimator among these estimators that are among the unbiased estimators that have minimum variance would be called as efficient estimators. So I am combining first two properties, unbiasedness and minimum variance. So if I have an estimator among the unbiased estimators, the estimator that has the smallest variance is called as efficient estimator, right? Among the unbiased estimators. So suppose I have a couple of estimators that are unbiased, then the estimator that has smallest amount of variance would be called as efficient estimator. So I am combining two properties of the estimator. So in fact, had theta been here, then all of them are unbiased estimators, right? Because all of them have expectation theta hat. So expectation theta hat 1 is theta, expectation theta hat 2 is theta, expectation theta hat 3 is also theta. But which is the better estimator among them? Theta hat 1. Because among the unbiased estimators, theta hat 1 has the smallest variance. Okay. So among the unbiased estimators, theta hat 1 is called as efficient estimator if it has a variance smaller than theta hat 2, where theta hat 2 is any other unbiased estimator, right? The next property is linearity, and an estimator that is a linear function would be called as a linear estimator. Say for example, when f of x is a linear function, then a estimator would be called as linear estimator. Say for example, your x bar, which is an estimator of population's mean, is basically 1 by n x1 plus x2 plus up to xn. So it's a linear function. It's a linear function, right? So I would also say that x bar is a linear estimator. Okay. The next property of the estimator is called as blue. Blue stands for, it's the acronym that stands for best linear unbiased estimator. We actually look for blue estimators. Yes?
So I did not quite understand the
Linearity is when an estimator is a linear function. Anything, fx is a linear function if on a graph it is on the straight line. So what you need to actually look at is whether f of x, that is giving you theta hat, is linear function. Say for example, x raised to p is not a linear function, right? But sigma x is a linear function. Estimator that is called as blue is best linear unbiased estimator. Now, what is best linear unbiased estimator? Best linear unbiased estimators are those estimators that are unbiased estimators, that have minimum variance, and that also have a property of linearity. So all the properties that we have discussed so far, if an estimator has, then we would call it a best linear unbiased estimator or a blue estimator. We look for blue estimators. Okay. Say for example, our OLS, ordinary least squares estimator of regression line, is a blue estimator. Okay. When we would take OLS estimators of regression line, which we would do as we go ahead and look at regression, that estimators are blue estimators. The last property that we would discuss is MSE. Okay, mean square error. Mean square error of a estimator theta, MSE of theta, mean square estimator of theta is expectation of theta minus theta hat square. Oh, actually other way around. We are doing theta hat minus theta hat. Makes little difference, but just to be consistent. Okay. So if we solve this, it comes to variance of theta plus bias of theta square. Okay. This is variance of theta hat plus bias of theta hat square. Okay. So basically this tells you how much of the we were looking at, when we were looking at minimum variance, only variance of theta hat, right? Here we also look at the bias that the theta hat is, and when we put bias and the theta hat together, what we get is MSE of theta. So we try to keep the variance smaller. We also keep the we try to keep the bias to 0. Okay, if not 0, then